Hello everyone. So ang ating lesson ngayon is based on chapter 7, and this is the start of our discussion on the Solow growth model and economic growth. So the following chapters will take us to the end of the semester na. And I just wanted to point out that these chapters can be very quantitative. So I would advise na tignan niyo yung end of chapter questions and sort of practice on the quantitative parts. As proof of that also, there are examples in the chapter itself which is quantitative na dadaanan rin natin. So that's sort of like the kind of questions you can expect. Now, see, economic growth as an idea, of course, is highly empirical as well. At some point, magdadala tayo ng empirical outlook dito. So for this week and next, we'll be focused on the theoretical component of economic growth. And then babalik tayo sa empirics and sa sort of the quantification of it. And then hopefully at the end, at the very, very end of the course, we will go to like growth strategies that are being used in different parts of the world, and different ways in which countries have figured out how to grow faster. And they're all of course based on the ideas of this ideas coming from this growth model called the Solow Swan economic growth model. Okay. So yeah, so that's our overview, and chapter 7 will start it, and then chapter 8 will complete this undergraduate level treatment ng Solo Swan model. We mentioned earlier that we were going to become more empirical, but for now, I just wanted to show some more information or some data. So I have here R, and I downloaded from the World Bank website some specific data on GDP growth and GDP per capita. So in particular, GDP per capita is here in local currency units. And I suppose I just wanted to show everyone GDP per capita ng Pilipinas. Okay, to start. Okay, so here it is. Just gonna make it a little bigger, like that. Okay. So what you might notice is, for instance, this shape looks very interesting. This is almost like a quadratic or an exponential growth curve na para mabagal siya to start and then it becomes faster and faster over time. Okay. So one way to very simply model this is to use an exponential growth over time. So parang, and in that sense, magkakaroon ka ng annual growth rate over time, right? The other thing here is you can see here the effect of the recession that we studied. Recall that in chapter just immediately before Solo growth model, we were talking about the Philippine experience, and one of the few times na nagkaroon tayo ng negative growth, and this is like one of the biggest, right? And the first real big one, okay, with negative growth. Subsequently, of course, there's been this one, and then this one, okay? And these are different instances of a recession and a problem. This might also be considered another one in the mid-2000s. Okay, and of course, this is the COVID shock here. And this is the 83-84 debt crisis, BOP crisis that we spent a lot of time on. If you notice, particular in this one, ang laki ng change, and our GDP per capita just literally fell by, just reading off the chart here, something like 20,000, right? Pesos. This is in constant LCU. 20,000 pesos in constant LCU pesos. I forget what the base year is. Probably here. Nandito sa mga 2018 probably base year. But we'll find out. We can find out next time. So ang laki ng change, and it's like a level change. Your GDP per capita literally sank like this. And then a lot of analysts have mentioned that it took almost 20 years. So this is 83, 84, and it will take until 2002, 2003 to go back to the real GDP that it was prior to the crash. So this is like the 20 years lost here, right? In which case, in order to make up this lost change here, your GDP per capita growth has to be much faster than it was before, right? But it failed to do that. So that's why it took 20 years, okay, to do that. So later on, we'll be talking a little bit about sort of changes in GDP per capita growth and how that could affect your standard of living. I also wanted to introduce the topic right now by looking at the Philippines specifically. And if you notice down here, let me just remove this one. Yeah. Down here, we are regressing the log of the growth rate to the year. And the coefficients here in this regression is meant as an annual growth rate figure. So for the entire series from 1960s, ba to? 1960s? Yeah, 1960 to 2022. So if you were to do that, again, this is to remind us that it's really an exponential growth that's driving it. So there's an exponential curve here, which corresponds to the coefficients of this regression. And what we've got, looking at the entire scope of the data, fills just the regression. Okay. So we're talking about a 1.5, 1.6% growth per year. We'll have more to say about the growth rate, okay, over time. But this includes essentially periods where the growth rate per year are faster and when it's slower. And of course, it incorporates these level changes here that will change the absolute level of the GDP even at constant or unchanged growth rates. One thing to think about, for example, I commented it out, but let's say kinuha mo lang yung data from after the, I want to call it the Great Recession, so after 1985. So we've got this. First of all, what you'll notice is the growth rate is faster, much bigger, right? And what you'll see here is if you apply that to the entire thing, mas malaki or mas steep yung red line. Okay, the red line now sort of hugs the top part, which tells you that yung growth rate post 1986 is in fact faster than if you were to look at the entire period here. Okay, but it's still not enough. It had not been enough to erase that 20-year gap here, in which it took us that long to go back to the levels prior to 1980. Okay, so we will return to a lot of this empirical stuff in a moment because the Solow growth model is in fact designed to sort of bring it to the data. So we'll definitely return to the Philippines and to cross-country comparisons of growth rate in a moment. All right, so now let's focus our attention on understanding the theoretical model here. So our task is to develop the Solow growth model. Chapter 3, if you recall, enabled us to describe how the economy produces its output. Okay, but now we'd want to make our model from chapter 3 more dynamic. And what we've got is a model designed to show how the growth in the capital stock, or K, growth in L, which are the two factors of production, and advances in technology, which will shift up the production function, will interact in an economy as well as how they affect a nation's total output of goods and services. So we'll build this model in steps. We'll focus really on capital per labor first and say that there is no, for simplicity's sake, there's no technological progress yet. And not even, at least in this first step, not even a growth in the labor force. Let's say you have a constant number for your labor force L. All right, so now let's go to the supply and demand for goods. So it will be quite similar to that of chapter 3. Here we focus again on what is in the classical model, our model of GDP or real GDP. Y is a function of K and L. We will assume that the production function has constant returns to scale, often considered a realistic model, right? Especially when all factors are able to adjust completely. So what that means of constant returns to scale is that if each factor grows by a factor z, then you can expect real GDP to also grow by a factor z. This means that if the z is 1 over L, so L is just a factor, right? L is just a number. So you can divide everything by multiply everything by 1 over L or divide by L. Then you've got y over L as a function of k over L and 1. We can actually write that out as this one. So what's just happened is we removed the 1, and because it's 1, it doesn't really matter. The small y is output per worker, and the small k is capital per worker. So what we can see here is that output per worker is a function of capital per worker. So what does that look like? We look at figure 4-1. And this is what it will look like. The production function shows how the amount of capital per worker K determines the amount of output per worker Y or F of K. The other thing that we're supposed to take away from here is the slope of the curve here is equivalent to what's called the marginal product of capital. It's something you've heard before. So that just means that if small k goes up by 1, output per worker goes up by marginal product of capital. And by the diminishing returns to the production function, that means that the size of MPK is falling as small k becomes larger and larger. Graphically, that means this line will become flatter and flatter as small k goes up. Next, we will think about the demand for goods and services. And this is basically a very simplified model of the one presented in chapter 3. Output per worker is equal to consumption per worker plus investment per worker. So the little letters are just the big ones divided by L. Each year, people save a fraction S of their income and consume 1 minus S. So consumption is just a function of Y, a constant fraction of Y is consumed. In that case, this equation here becomes this one down here, replacing consumption. And what you'll find is that investment is equal to S of Y, right? And this is super familiar because this is just the I is equal to S. The S times Y, or small y, is basically the savings per worker, which is equivalent or equal to investment per worker. So that's S equals I in this closed economy model. All right. So growth in capital stock. So this is the key concept of a growth model, right? Recall that in chapter 3, and in fact, all of the models, all of the chapters, all the models in all of the chapters, all of the factors of production are fixed. But right now, what we're thinking about is what happens if we can expect or we include the notion of the growth in capital stock per worker. So as you can see, an increase in small k will also increase y over L, or small y. So this is the growth that we are talking about. So for any given capital K, the production function Y determines how much output the economy produces, and the savings rate S determines the allocation of that output between consumption and investment. S% goes to investment. So here's the growth in capital stock. So investment is the expenditure on new plant and equipment, and it will cause the capital stock to rise. So investment is the key variable for which growth is possible, and growth is coming from an increase in the capital stock per worker. Depreciation is the wearing out of old capital, and it makes small k go down over time. So those are our two forces. Investment pushes it up, and investment is just fixed share of total output or GDP. And depreciation is just, again, a percent of old capital that's wearing out. So we mathematize all of this by saying investment is this one, S times F of K, where F of K is, again, the production function that we just talked about earlier, the one that exhibits diminishing returns to K. And look at what we've got here. This is output, the green line, F of K. Investment is S, F of K, where S is less than 1. So the red is just shifted down version of the F, or the green one. But at any given K, the difference between Y and investment is simply consumption. So remember, Y equals consumption plus investment. So that's it for any given K. So you can do the same thing up here. Up here naman, the I is this, and then consumption is, whoa, way bigger, right? So the higher the K is, the higher your Y is, and then the higher your investment and your consumption is. So everything is growing as K is growing. What else? To incorporate depreciation, we can assume that a certain fraction delta of the capital stock wears out each year. Here, delta is called the depreciation rate. If capital lasts an average of 25 years, then the depreciation is 4% per year, or 0.04. Okay, so let's look at 7-3. Look at depreciation. Since this thing is just a number, so what we're drawing here is the function delta K, right? And the slope of this is equal to delta, whatever delta is. So it's a fixed slope. Depreciation is fixed as a function of K. The more K there is, the more K of it, the more delta K of it will depreciate. Okay, so we've got the two forces, right? Investment makes capital grow, depreciation makes it go down or shrink. Therefore, the change in capital stock is just sort of the sum of the two, I minus delta, right? I minus delta K, I should say, I minus delta K, where I makes K go up and delta K makes K go down. That's why it has a minus sign. Another way to put it is the delta K equals SF of K, because investment is just a fixed function of capital, minus delta K. So the first thing that should pop out here is everything is a function of capital, as capital per worker. And because of the shapes of these functions, there is a K where the change in capital stock is 0. There's a range of K where this change in capital stock per worker is positive, and then there's a K range of K for which this is negative. And in fact, we can refer to figure 7-4 for exactly that. So if you forget the bottom text for a while, look at the red one. That's the investment. The depreciation is the blue one. What this shows is that there are Ks, there's a range of Ks for which investment exceeds depreciation. There's a range of Ks up here where depreciation is above investment. And therefore, if there's a place where it's positive and there's a place where it's negative, there's a place where it's 0, where exactly they're equal. Okay. So now let's refer to the text. This is K star, the K star where the investment equals depreciation, and therefore delta K is equal to 0. So capital per worker is not growing. That's what delta K means. Capital per worker is not growing. So if the capital per worker is less than K star, mas malaki ang investment kaysa depreciation. So you expect capital per worker to go up, because the forces pushing up capital per worker is greater than the ones pushing it down. The opposite is true here. If there's too much capital per worker, this basically will mean investment is not enough, depreciation is too much, and that therefore on net, we are moving left towards K star. K star, by the way, is called the steady state. Steady state because that's a value of K, or capital per worker, for which capital per worker is not growing anymore. So that's why it's a steady state. So approaching a steady state, here's a numerical example. So this is the numerical stuff that I was warning everyone about. So here is your Cobb-Douglas production function. K raised to 1/2 and L raised to 1/2. So all we're going to do now is to implement the math. So this is y over L, and you're dividing everything by L. And if you follow the math here, then it becomes small y equals small k raised to 1/2. And if you're ever familiar with this kind of functional form, this is just, again, something that is concave. That's something that's growing, but it's growing at a decreasing rate. So it's written as this one. So it's a much nicer way of writing k raised to 1/2. So let's do the example. For example, we begin by looking at the production and allocation of output in the first year when the economy has 4 units of capital to start. According to the production function, y equals the square root of k. There are 4 units of capital, so that produces 2y. 30% of y is saved and 70% is consumed. Because 10% of capital stock depreciates, delta K is 0.4, an investment of 0.6, and a depreciation of 0.4, and the change of capital stock is 0.2, right? So I minus delta K is 0.6 minus 0.4. That's why the delta K is, the change in K is 0.2. So this argument here, string of steps here, I mean, comes from, can be seen here, dito sa table 7-2. So here's our assumptions. Here's our production function in capital per labor form. S is 30%. Depreciation delta is 10%. Initial capital per worker is 4. So 4 and then 2. Square root of 4 is 2. Consumption is 1.4. Investment is 0.6. Notice that this sums to 2. Delta K is 0.4, right? So 10% of that. The change in K is S of Y, which is 0.3 of this, that's 0.6, right? Investment. Minus this one, investment minus this one, that's 0.2. 0.6 minus 0.4 equals 0.2. So you can do it for each line here, and at some point, it's going to move up slowly until it reaches the steady state capital per worker of 9. And once it reaches this level of capital per worker, the change in K will become 0. And in fact, if you notice here, the change in K is largest at the start, and then it's falling and falling and falling. So you can imagine that the growth rate of GDP per worker is sort of falling as closer you get to your steady state. Okay, so let's go back to the math. Again, here is the thing that defines the steady state. 0 is the delta, or the change in K, I should say. Change in K is 0 equals investment minus delta K, which is depreciation. So you can solve for K here. And this next line just substitutes this one for the assumed form of your intensive or per capita or capital per worker production function. And that's just this. You can square both sides, finalizing everything, and K star is equal to 9, exactly what the table says. K is equal to 9. All right, so now we think about how savings affects. So recall that the savings rate will determine investment. The more you save, the more you invest, because S is equal to I. So the model shows us that the savings rate is a key determinant of the steady state capital stock. If the saving rate is high, the economy will have a large capital stock and a high level of output in the steady state. If the saving rate is low, the economy will have a small capital stock and a low level of output in the steady state. So this is what we are talking about. So think about S1 as the initial, right? And that's this sort of pink curvy line here. The depreciation line is still the blue one, delta K. And the intersection of delta K and S1 FK is this one, for instance. And the question asks, what if tumaas ang savings rate? Kung tumaas ang savings rate, what will happen is this curve here will go up, right? Exactly by whatever increased S is. Remember, S is bound to 1. So the largest S is if it's equal to the actual production function. But that also means that you're not consuming anything, because if you invest everything, that means your consumption is zero. Now, if S moves from some number to another number less than 1, what we will expect is investment will be higher because savings equals investment. But also, you're going to increase your capital per labor from whatever it is to whatever the new steady state is. You will cause capital stock to grow to the new steady state. So a higher savings rate will mean a higher investment, which means there's a force to push your capital per labor to a higher number. And that's coming from this picture right here. All right. Golden rule of capital. So you might imagine if S going up is a good thing because Y goes up, investment goes up, and so on, right? Um, why is that bad? Well, like we just mentioned, I goes up, um, if I goes up, what will happen is consumption will initially go down exactly by the amount of the increase. So that means you've got a lower consumption level, right? And in the long run, you'll also have a lower consumption level, as you'll see in a moment. So what we're going to look at here is in the golden rule. So let's read it a little bit. So far, we have used the Solow model to examine how a savings rate and investment determines its steady state. Okay. Right. The equation uses the Solow model, second paragraph, to discuss the optimal amount of capital from the point of consumption, which is economical being. So there is an S, which will sort of maximize the steady state consumption that we will enjoy. All right. So the steady state value of K that maximizes consumption is called the golden rule of capital, and we will call that K star gold. The important thing to note is K star gold is never going to be the same as K star. And K star is the one that will make delta K equal to 0. So that's going to be different. So to do this, we will use this GDP equation here, y is equal to C plus I, and rearrange it such that C is equal to Y minus I. So C consumption is just F of K, which is Y, minus delta K, because um at the steady state, delta K, right, is in fact equal to investment, right, at the steady state. So if you substitute the production function for Y and delta K star for I, you can write steady state consumption as the following, right? And the question is, what is the K star here? What is the value of K star here that will maximize this? And what you should be doing is to get the first derivative of this expression here. And that's going to be the way to get K gold. Okay. You can see that here in the graph. So this line, this green line here is F of K. And then you're subtracting investment right here, which is steady state depreciation, which is delta K. Okay. As you can see, there is a K gold for which consumption is maximized. And the way to do it mathematically is to, at this K star gold, the slope of F of K is equal to the slope of steady state depreciation, which is delta. So the golden rule K star is determined by MPK equals delta. So this will determine K star, which will give you the golden rule level of capital per worker. At the golden rule of capital, the marginal product of capital net of depreciation is equal to 0. So MPK minus delta is equal to 0. And you, as the analyst, can use this condition to determine what the golden rule capital stock is for the fund. Okay. So this picture, 7-8, I think is the most important picture that will sort of explain to you what the difference is between the steady state K and the golden rule level of K. So typically, right, what's going to happen here is this is C star, right? Because at this K gold, okay, at this K gold, here is your Y. And as we can say, the difference between Y and investment, or in this case, S times F of K, is equal to C, because C plus investment equals Y. So this is C. And this is investment. And as you can see, there's an S which delivers this K, right? So changes in S will lead to changes in K, right? And you can draw different S's, and different S's will have different K stars, but those K stars will not be K gold, because K gold is calculated as the K where the slope of F, which is the marginal product of capital, equals delta K. So this black thin line here has the same slope as the delta K down. So this in fact tells you that there is a special savings rate for which the steady state capital per worker is in fact equal to the golden rule level of capital per worker. So if you can draw another S, for instance, like this, iba ang magiging K star niya, and iba rin ang consumption and investment, and it's not gonna be the golden rule. There's only one K that satisfies the golden rule, but potentially many, depending on whatever the savings rate is, many Ks are associated with the change in K equal to 0, because there are possibly different S's. And going back to my original point, in order to achieve K star gold, you need to have that special savings rate, which will move this red line up and down such that you achieve this K star gold. All right, so we can calculate the K star gold. Let me just check if I'm forgetting anything that's cool and important. Keep in mind that the economy does not automatically gravitate toward the golden rule. If we want any particular steady state capital stock, such as the golden rule, you'll need a particular savings rate to support you. This is exactly what I'm saying. A different savings rate will lead to different capital per worker steady states, right? But those may not necessarily will usually not be the golden rule steady state. And there's also unique S that creates that K, which leads to maximize the consumption. Okay, so now we will do this numerical example. So here we have the same reduction function. And here you have S over delta, right? Notice that we're not gonna insert a value of S because S is the thing that we need to know, right? And everything else we will input. So basically what this is saying is that K star is a function of S. The larger S is, the larger K star is. The smaller S is, the smaller K star. So S and K are directly related. So what is the golden rule? Well, if you recall, the golden rule involves calculating MPK and setting that equal to delta. So the marginal product of capital is this one, which I'm sure you all know how to do it. Something as simple is easily almost always taught in a calculus class. So ito yung marginal product of capital. Under this formula, you equate marginal product of capital to delta. Okay. Is that here? Marginal product of capital, marginal product of capital minus delta. That's 0 when S is 0.5. Because recall that S and K are the same. So recall that this K star, all you need to do is to substitute K star, this one to here, and MPK will now be a function of S. And this table here tells you that you'll need an S of 0.5 in order to achieve the golden rule level of consumption. Now remember, an S will lead you to a specific K, and the K here is calculated from MPK minus delta. That's the golden rule level of K. And now we talk a little bit about transitions to the golden rule steady state. And this is quite general. This can be transitions to any new steady state. If you start with too much capital, this is what it will look like. First, consider a case when the economy begins with more capital than it would have in the golden rule steady state. That means capital must fall. It must reduce savings in order to reduce the capital stock. So what's going to happen is a reduction in savings will lead to an immediate fall in investment and an immediate increase consumption. But then because K is now negative, K is small, going down faster. And therefore Y is going down. So if Y is going down, consumption must be going down after the initial increase. And investment itself must also be going down after the initial decrease. So that's starting with more capital than the golden rule. What happens if you start with little or too little? Okay, what will happen is you will change the S such that you'll hit the target golden rule value, okay, which is again larger because you're starting with less capital than the golden rule. So you're moving towards a higher capital per worker. So what will happen if you're doing this? You are going to save more. So there's going to be a jump initially because you're saving more. Consumption will fall. Exactly. This is the mirror image, same size. Kung ano yung nawala sa investment, kung ano yung nag-gain sa investment, yun yung mawawala sa consumption. But then as K is going up, because now you're starting at a K less than the golden rule, but you're going to rise over time. What's happening is Y per output per worker is rising. Consumption is also rising because Y is rising, and investment is rising because of Y is rising, right? Because recall, investment is just a fixed fraction of Y. Okay. So before we move on to the end, right? This is to the end of the theoretical mathematical portion. So now we will assume that population is growing. So let's suppose that we'll keep everything, right? K is K, small k is K over L, and small y is Y over L. Now, the number of workers is now growing over time. So the change in capital stock is now change in K minus I investment, which tends to increase K, and then delta, which tends to lower small k, and N which will tend to lower capital per worker because the more laborers you have, the denominator will grow, and that's why K over L will go down, mechanically speaking. So this equation shows how investment, depreciation, and population growth influence per worker capital stock. Investment increases K, whereas depreciation and population growth both decrease small k. You can think of the term delta plus NK as break-even investment, the amount of investment necessary to keep the capital stock per worker constant. Yeah, siya break even. I would also suggest that this is equivalent to the steady state again, because steady state essentially means that capital stock per worker is constant, and because K over L needs to be constant, and remember now the denominator is growing at rate N, so that means the numerator, so big K, must be growing at least as fast as depreciation and more because there's L. So it has to grow by as much as the denominator is growing. Right? So K over L. If K over L is constant, that means the numerator must be growing as fast as the denominator. So that's why. All right. So our analysis with population growth now proceeds as much as it did before. So here is your equation for the change in K, which is again investment minus the break-even or the steady state level of K here, which is now a function of both delta and the growth rate of labor. The picture is largely unchanged except for the blue line is now delta plus n. So you can imagine differences in n will make this line steeper or flatter. So an increase in n will make it steeper. A decrease or a fall in labor growth rate will cause a lower blue line here. Also, we can take a look at what happens if you shift the blue line up and down. If you're going to shift it by an increase in n, then that means an increase in n, or the growth rate of labor, is associated with a decrease in K star, a fall in K star. And if K star goes down, then Y star, or the steady state Y, will also fall down. Similarly, if delta plus n pivots to the right, that means n becomes smaller. That means your K over L, or your small k, will become larger here, and your Y over L will also become larger. Okay. So here's the effects of population growth. Oh, we already talked about this. This is an increase in the rate of population growth from N1 to N2 will pivot really. It will pivot the blue line up, and then it will decrease capital per worker from K1 to K2 star. All right, so here we go. C is equal to Y minus I. And C star is equal to this one. So now we're thinking about the golden rule. And we're going to try to maximize consumption. Maximizing consumption is just the first order condition of this thing. So you get marginal product of capital, which is the first derivative of this one. And then delta plus N is the derivative of delta plus N times K. So now instead of MPK is equal to delta, the golden rule will become MPK equals delta plus N. Okay, because now you have a new factor here, which will tell you how much capital should be growing in order to reach that steady state where consumption is maximized. So kailangan you have to account for the changes at N. So the golden rule steady state, the marginal product of capital net of depreciation has to be equal to population growth instead of 0. All right. So that's the mathematical part of this chapter. I would highly advise, we'll go through the rest of this chapter. Of course, we're not done with the ideas. But I wanted this particular recording to focus on calculations. So I would suggest you guys look at this one, which is again cribbing from the main text. K raised to 1/2, L raised to 1/2. And I would suggest practicing getting the steady state for any arbitrary savings rate. And finally, calculating the golden rule, which requires you to find that savings rate, which will hit that K star, which will maximize consumption per worker. And you should do this for the general case. What's the general case? The general case is when N is not 0. Because if you take a look here, this is exactly the same as the simpler case, except that N can be 0, right? If N is 0, then MPK is equal to delta. Similarly, to find K star, right? You could imagine N being 0, and this essentially becomes the previous equation, right? So this, in a sense, is more general because it allows for N to be not 0. So you should practice getting the steady state using this equation here, or this equation, and the golden rule, which you will get from this equation. Okay, and the only question is, what is the S that will make K star equal to this condition, right? So that's the mathematical component of this. All right, so I'll see you guys on Thursday. All right, thank you very much.